Okay, this is Stoichiometry Part 1, and this is going to cover mole to mole and mass to mole conversions when calculating um, the various weights of products and reactants in a reaction. So, let's get started. In class, we talked about how stoichiometry is kind of like following a recipe and calculating if I have 5 batches of something, or if I'm repeating the same process over and over in the kitchen, then I'm going to change the quantities of my ingredients, and that's going to change and affect what I get out in the end. So it's the same thing as in stoichiometry. So, for example, you have this cookie recipe, and the question is, how much baking soda do I need if I make 3 batches of this? And so you just multiply the quantity for baking soda, which is 1/4 teaspoon, by 3. So you use 3/4. And then flour, the same thing. So you're kind of using these amounts are dictating and controlling everything about this recipe and how much you need. If you want to triple or double it, then everything is determined based on the ratios of these ingredients. Okay, so that's important, and that's kind of going to tie into everything we do in stoichiometry. So again, if you didn't get this in class, you might want to jot this down now. Stoichiometry deals with mass relationships between reactants and products. So just like ingredients in your recipe, I want 3 times as much flour as this ingredient. Stoichiometry is dealing with the same thing. I want 3 times as much aluminum as I want oxygen in this reaction. Okay, so we can use that to calculate how much product to expect or how much reactant to put in. Remember the airbag principle. In airbags, we need to know how much gas to expect to come and fill the airbag, and we need to know then how much reactant to put in to the steering wheel so that my airbag works perfectly. Okay, so the first step is going to be kind of interpreting chemical equations. So remember, we get these we get these descriptions of a reaction, like nitrogen gas reacts with hydrogen gas to form nitrogen trihydride, or ammonia is the shorthand name that we call it. So the first step is, when you approach a problem like this, is you got to translate that from words into equation. Okay, so all the naming and nomenclature rules apply, including Hofbrinkel. That's going to be the area that you get tripped up on, is forgetting to make a diatomic molecule and just leaving it as one, and don't do that. Okay, so nitrogen, hydrogen, and you make nitrogen trihydride. So use all your naming rules, and after you balance the equation, you get this. Nitrogen is a 2 because of Hofbrinkel, the H in Hofbrinkel, so both of these are diatomic, and then nitrogen trihydride, 1 N, 3 H's. And then when you balance, 1, 3, 2 should be your coefficients. Okay, so that's going to be our first step, is interpreting description into equation. So here's a list of info that you can extract from that equation. So just from that one reaction, you can tell me the number of particles of each of everything being used, the number of moles, the masses of each of those products and reactants, and the mole ratios of what I'm doing. Like, I need 3 times as much of this and this. Okay, all of that can be extracted from a chemical reaction. So let's look at the first big thing that we need to know is moles. Moles is maybe the most important part of stoichiometry, because moles is what makes everything possible. So when in doubt, you're always going to rely on moles and fall back upon calculating the moles in a reaction. That's always going to be your fallback option if you ever get stuck. Just remember to go with the moles. So here you have your reaction. Okay, so how do I find out how many moles I have from just this equation? Well, the answer is that these numbers, the coefficients, are the moles. So in this reaction, what this means is 1 mole of nitrogen reacts with 3 moles of hydrogen and gives me 2 moles of ammonia, or nitrogen trihydride. Okay, so when you ask for moles, or if somebody says, hey, how many moles are in this? How many moles of hydrogen? Well, you know right there, 3 moles of hydrogen. That's what these numbers mean. So you didn't know that, but now you do. So the next thing is mole ratios. So a ratio, all that is a fraction, a comparison of two quantities. So for instance, in the class, if there's 5 boys and 4 girls, the ratio of boys to girls is 5 to 4. So all it is a fraction. You can express that as 5 to 4, 5 colon 4, 5 divided by 4. All of those are valid examples of ratio. So in this reaction, if I want to know the ratio of like nitrogen to hydrogen, then I just say, well, there's 1 mole of nitrogen for every 3 moles of hydrogen, right? And that's just coming from the mole coefficients over here, 1 and 3. So nitrogen to hydrogen, there's 3 times as much hydrogen as nitrogen, okay, 1 to 3. Ammonia to nitrogen, there's 2 moles of ammonia for every 1 mole of nitrogen. So for every 1 mole of nitrogen I put in, I get 2 moles of ammonia out. And then lastly, for every 3 moles of hydrogen I put in, I get 2 moles of ammonia out, okay? So remember, you might think, oh, this does not follow conservation of mass because 1 plus 3 on this side is 4, and you only get 2 moles out. But remember that ammonia weighs a lot more than nitrogen and hydrogen, okay? So mass is conserved. Moles are not conserved. It's not the law of conservation of moles. It's the law of conservation of mass. So while I have 4 on this side, I can have 2 on this side because guess what? This is going to weigh twice as much as these guys. So it's okay. So that kind of brings us to the point of when are we going to use mole ratios? Well, we're going to use these ratios in dimensional analysis because if I know how much grams I have of one thing, then this is going to allow me to calculate grams from here to go all the way to grams from here. So here's an example. How many moles of oxygen are produced when 3.2 moles of potassium chlorate decomposes? The other product is potassium chloride. Okay, so they're making us do all the work and they're making us come up with the reaction ourselves. So pause the video, you know the drill, pause the video, balance the reaction, come up with what you think it is because this is practice. You got to be able to do this. So unpause this when you're done. Okay, so this is what you should have got. And this is actually the same reaction that we did in class with a gummy bear when it exploded. Okay, so I took potassium chlorate, and that's KClO3, and when it's heated up, it decomposes into oxygen and potassium chloride. Okay, when you balance it, you get 2, 3, and 2. So I want to know how many moles of oxygen are produced over here when I use 3.2 moles of potassium chlorate. So if I have 3.2 of this guy, how many moles of this guy am I going to get? Well, the ratio is 2 to 3, right? So you could work it out in your head. I'm going to use dimensional analysis because that's the way that works for me. So I start off with what they gave me, right? 3.2 moles up here because that's what's in my problem of potassium chlorate. I'm going to always give the formula because I am changing moles of one thing to another and I don't want to confuse myself. So I'm always going to say moles of potassium chlorate. So 3.2 moles up here. Then what goes down here? If moles of potassium chlorate's up here, moles has to go on the bottom. How many moles do I have in my reaction? I use 2 moles, right? So here's 2 moles of potassium chlorate. Okay, and 2 moles gives me how many moles of what? I want moles of oxygen. So 2 moles of this gives me 3 moles of oxygen. So this is where that ratio comes into play, right? 2 gives me 3. So 2 gives me 3 moles of oxygen, okay? That's what I want to find out. So I'm done. I multiply 3.2 times 3 and divide it by 2, and I get 4.8 moles of oxygen. So there's my answer. Okay? Here's another example. How many moles of water are produced if 15 moles of oxygen are produced in the above reaction? Let's say I measure 15 moles of oxygen are given off, and now I want to say, well, how much water did I get then? And this time they gave us the reaction, which is nice, okay? So again, my train track, I start off with what they gave me, 15 moles of oxygen. There you go. So now look up here. I want 15 moles of oxygen on the bottom to cancel out, right? So how many moles do I have up here? Just one, okay? And that gives me, my mole ratio is for every mole of oxygen, I get 4 moles of water. So there's that, okay? So I want moles of water, so I'm done. There's my moles of water at the end. So 15 times 4 divided by 1 is 60 moles of water. So yeah, that's pretty easy. And I think the entire front page of your worksheet that you're supposed to be doing is just problems like this, okay? On the back, though, we mix in getting mass, which is just an extra step. So let's look at what happens if I also want to calculate mass on top of that. Okay, so hydrogen and oxygen gas are burned to produce water or make water. So what mass of hydrogen is required to produce 35 moles of water? Okay, so you're going from mass to moles. And so immediately what you should think about is GMMAA, right? Grandma's massive moles are atrocious, because you're going to be going from mass grams to moles, which means you're going to be using eventually this thing called molar mass off your periodic table, right? So when we write our equation, oxygen and hydrogen are both diatomic from Hofbrinkel. So when they react together to make water, it's going to look like this, right? When you balance, you get 1, 2, 2. So here's your track. Let's go. What did they give me in the problem? They gave me 35 moles of water. Sorry, that's a typo. Required to make 35 moles of water. Yeah, just 35 moles, okay? So that goes right there, 35 moles of water. So now just follow your train wherever it goes. I want moles of water to be down here. How many moles of water do I have in my equation? 2. So 2 moles of water gives me how many moles of what element should I be looking for? Well, they want the mass of hydrogen. So let me look at moles of hydrogen. 2 moles of water gave me 2 moles of hydrogen, okay? So am I done? Well, this right now will give me moles of hydrogen, but I don't want moles of hydrogen. I want the mass of hydrogen, okay? So I got another step. If I'm going from moles and I want to get to grams to mass, I got to use this thing called molar mass, right? So what is the molar mass of hydrogen? 1 mole of hydrogen is how many grams? Well, look at your periodic table. Hydrogen weighs 1 AMU, and so the molar mass, since there's 2 hydrogens, is going to be 2 grams. So I add on another car. 1 mole of hydrogen gives me 2 grams of hydrogen. Okay, awesome. So now I'm left with grams of hydrogen, which is what I want. So I cancel. 35 times 2 times 2 divided by 2 gives me 70 grams of hydrogen. Okay, so it's a little more tricky because you're adding on an extra step, but the same principle is happening. Remember, I said moles are always your fallback. If you don't know what to do, you started with 35 moles of water, you just convert to moles of whatever you're looking for, so hydrogen in this case. And then after that, you use that second step to get to grams. Okay? So here's another one. Hydrazine into H4 is used as rocket fuel. Reacting with oxygen, it produces nitrogen and water. So what mass of oxygen is going to be needed to burn 100 moles of hydrazine? Okay? Because in space, guess what? There is no oxygen in space. I don't know if you knew that, but there isn't. So any oxygen you use for rocket fuel to burn, you have to carry with you in a separate tank. That's why every rocket and everything that NASA sends up has to have a liquid oxygen tank, because to burn your rocket fuel, you got to supply your own oxygen in space, buddy. You don't got free oxygen like you do on Earth. You got to carry it with you. So how much are you going to put in your tank? Well, let's find out. I know I'm going to use GMMAA because I'm going from moles of hydrazine to mass of oxygen. Okay, so here's my equation. Hydrazine plus oxygen makes nitrogen gas and water. Remember, Hofbrinkel is going to get you O2 and N2. Both of those are diatomic. So here's my train track. They gave me, as my starting info, 100 moles of hydrazine. So here's 100 moles. So how many moles do I have in my equation? Well, just one. 1 mole of hydrazine. And that gave me, what am I looking for? Well, I want oxygen, right? So 2 moles of oxygen. Okay. Now I want mass of oxygen, so I need to convert moles to mass. When I look up here, to get from moles to mass, I use molar mass. So the molar mass, 1 mole of oxygen weighs how much? Well, you got 2 oxygens. Each oxygen is 16, so 32 grams of oxygen. Okay. Now I'm done because I want grams of oxygen, and that's what they asked for. What is the mass of oxygen? Okay. So 100 times 2 times 32 divided by 1. So that gives you a whopping 6,400 grams of oxygen. Okay, so that's a lot, but that's what you got to have on your rocket if you want to use up all your fuel, which why would you want to waste your fuel? You want to use that all. Okay, so that's the end of the video. Due on Monday or Tuesday, January 14th or 15th, are your notes over this video, and there will be a note check, and your homework sheet completed with their practice problems. And the name of that is, it says at the top, Practice Problems, Ideal Stoichiometric Calculations. It's a mouthful, but you can do it. So I'll see you then, and have fun.